Okay, this is 3.6. First problem says you invest $1,000 on January 1st. Your investment returns 6.25% compounded monthly. How much we have on June 30th? Okay, so the formula we're going to use for that is on the formula sheet. It's the formula that we use for compounding a certain number of times per year. And we're going to use 12 for that because we're compounding monthly. The interest rate is 0.0625 or 6.25%. And we're calculating it 12 times. And then the time that goes by from January 1st to June 30th would be 8 years, but then there's another 6 months from January 1st to June 30th. So really we have to do 8.5 years. And then the amount we start with, if we invest $1,000, would be 1,000, plug that in, and it gives us our answer of 1,698.71. Okay, for the next problem then, let's go back and use the variable. This is our equation, and it says you will have at least 15,000. So let's find out when we have 15,000, or at least that. Solve for t here. So divide by 1,000 and take the log of both sides. So if we divide by 1,000, we can get rid of 3 of these zeros. And I would, I don't know. I mean, there's different ways to do this, but I guess it's probably easiest just to take the log of both sides here, and then bring the exponent down. So when you bring the exponent down, it's 12t. And then divide, so you have log of 15 divided by log of this, whatever this value is. And that's going to give you 12t, and then divide both sides by 12. So, we could put 12 here if you wanted to, multiply by 1 over 12 instead. But so that's what you need to plug into your calculator. There's different ways to solve this, but make sure you can solve this equation to get t. 43.4415. So that's 43 years, and then 0.44 of a year. So if you take this decimal, 0.4415, and multiply by 12 months, you'll find out that's 5.298 months. So that's May would be 5. So after May, so we'd have to say June. After June then, because in the month of May, you'd have more than the amount they wanted, which was 15,000. So we'd have to say June, and then 43 would be 2,043. It's a little tricky, but that's the month and the year they want. The next problem says $7,000 invested in a bank account with an interest rate of 10% per year compounded continuously. So the continuous formula is some amount times e to the RT. So we're going to invest $7,000 there times e to the 10% per year would be 0.1 times t, and we want to know when that's going to be equal to our other formula, which is compounded in this case annually, which is 1 over, well, if annually our n value is 1, but here's the formula we're using there. So that'd be, we start with 16,000, times 1 plus the rate of 5%, 0.05, compounded annually, so it's just 1 time per year, so I don't need to write that, I can just write 1.05. To the 1 is n, the number of calculations per year, times the number of years t. So this is the equation we're solving right here. Now, you can graph this if you want. If you want to pull up Desmos and graph this, you'll get the solution is like 16.14. That might be the quickest way to do it, but there is another way we can solve it algebraically. I know it's a tough one to solve, but I would divide both sides by 7,000. That gets rid of, makes it 16 over 7 here. And then I would take the natural log of both sides, or change it into log form, however you look at it, log base e of this equals 0.1 t. I would then, before you drop down to t, you actually have to do this, which is kind of confusing, but it's actually the log of two things multiplied together, so I have to make it log of the first thing plus log of the second thing before I bring down this exponent. Use the exponent rule. But I can bring down this exponent now, so I have natural log of 16 over 7 plus t, natural log of 1.05 equals 0.1 t. I would then subtract this from both sides, so subtract t, natural log of 1.05. And these are actually like terms, right here, because you have t to the first there. So you want basically 0.1 minus natural log of 1.05. No, it's just tricky. Or actually, I'll do this. I'll factor out t, and so you'll have 0.1 minus natural log of 1.05, and divided by this quantity right here. Whoops. Right there. So then my answer is this quantity right here in the calculator. I know it's tough to plug in, but if you do, plug that in correctly, you will get, what was it, 16.14 about. And I think I just entered in 16 years because it happens in the 16th year, and that seemed to work. Okay, the next problem says you invest $860 at 5% annual interest. Okay, so once again, our formula for simple interest is P times 1 plus R over the number of calculations per year raised to the number of calculations per year times the number of years. Now, this is annual interest, and it's just 1. So that simplifies the formula a little bit. Becomes this. 860 is what I'm plugging in. It's 5%, so it's going to be 1.05. And then we just have to raise this to 1. Do this in your calculator, then change it to 2, and then change it to 10. If you do that, you get the answer 903. And then what's nice is you can take, once you plug that in your calculator, you can go up and grab it again, and just change the exponent, to 2, and hit enter. Do the same thing. So that's 948 to 15. And then same thing, go up, grab it, and change the exponent to 10. And that gives you 1,485 cents. All right, next problem is you're investing money at 10.3% annual interest, so A equals PE to the RT. It's compounded continuously, so I'm using this formula. And then how long will it take for your investment to double? So let's find out when it's going to be equal to 2P. And it's 0.103 times T. So we're solving this for T. Obviously the P's cancel. So we have 2 equals E to the 0.103T. And we can change it into log form. So log base E of 2 equals 0.103T. Divide both sides by 0.103. And you get this for T, which is 6.73 years, rounded to the nearest hundredth, and that worked. Okay, this problem says Dan has a choice of investing a sum of 4% compounded monthly or 3.5 compounded daily. So once again, the equation we're going to use for a finite number of computations in finance is this equation for interest. So we got to look at our interest rate here. We're going to looking at this effective interest rate once we simplify it. We have 4% compounded monthly, which would be this. And we're comparing that to, over here, 3.5% compounded daily. So that'd be 365 raised to 365T. What I'm going to do, I'm going to simplify this number right here and look at that interest rate. So if I do that in my calculator, if I do 1 plus 0.04 divided by 12 to the 12th, that gives me 1.04074 and 1.0356. So I would enter in the effective interest rate for the first one is 4.07. And for some reason they wanted a third decimal place on that. I don't know why. And then this one, 3.56 seemed to work. So as long as it's within 10% of the answer, I believe it works. But looks like we got those two answers. Okay, the next problem then, it says over 10 years, the original principal of, I don't know what this 36 is doing there. That's a typo, must be 1,022 accumulated to 2,420. And it was compounded monthly, determine the annual percentage rate. Well, we have a formula for that. That formula is the amount of an investment equals the principal times 1 plus R over the number of times it's calculated per year raised to that number times T. So it started with 1,022, ended with 2,420. The rate is 10%. I'm sorry, actually we're looking for the rate over the number of times it's calculated, which is 12 times per year, per 10 years. So we're solving this equation where this is 120 then. We're going to divide both sides by 1022. We're going to then raise both sides to the 1 over 120. That gets rid of the exponent. We get this number equals 1 plus r over 12. And this number in your calculator gives you 1.0072. So when you subtract 1, you get 0.0072. And then that equals r over 12. So you multiply both sides by 12. And that gives you a rate of, in my case, 0.0865 or 8.65% for my annual rate. Next problem, what's the effective rate? That's equivalent to the nominal rate of 18% compounded monthly. Once again, we use this. And we need to simplify this a little bit. This is 1 plus, it's 18% compounded monthly. So n is 12. Now we can simplify this to get it to p, and then, 1 plus r to the t is basically what we're trying to simplify that to, because that'd be like an annual percentage yield. So let's simplify this quantity right here. It gives you p times, when you simplify this, if you do 1 plus 0.18 over 12 and then raise that to the 12th power, 1.1956 to the t. So you can see it's actually like multiplying by 1 plus 0.1956 a certain number of times. So you start off with some principal and you multiply by this number however many years you have. So that's actually the amount right here that you're adding. That's actually your effective rate, which is 19.56%. Okay, the next problem, we're going to borrow $4,400 from the bank to buy a piano. We're going to pay it off equal payments at the end of each week for 2 years. The interest rate is 6% compounded every week. Determine the size of the payments, the total interest paid. All right, now we've got a formula for this in our book we could use. It's not hard to use plugging in, but we also have these time value money calculators on our calculator, which to get to them, you could get an app on your phone or find one on the internet. But in our calculator, if we go to apps, click on finance, we've got a time value money solver on the calculator. So let me run through this with you. N is the total number of calculations, total number of payments, which is 52 times 2 in this case, because it's 52 payments a year for 2 years. It's 104. The interest rate is 6, and I want you to enter it as a percentage, so its interest rate as a percentage is 6%. We start off with the principal value of $4,400. The payment we're going to calculate, I'll show you how, so just ignore that, but that's already there. Let's say it's 0 for now. The final value, we're going to get to 0. The payments per year is going to be 52, because it's we pay every week, so that's 52 payments a year. Calculations per year is 52, it's calculated every week. So enter that all in, and then put your cursor on payment and hit alpha equals, and that will give us the payment amount that we would need in order to get this final value to 0 with these conditions. That's $44.92 for a payment. And I would then need to multiply that by the total number of payments. So $44.92 times 104, which gives you $4,671.68. That's how much I pay total. Obviously, if you subtract the amount that you borrowed, $4,400, you get the remainder of the amount that you had to pay in interest, which is $271.68, and that goes right here. All right, next problem then, $20,000 per down payment. House is priced at $176,000. Interest rate's 8% compounded monthly. Determine the size of the monthly payments to pay it off in 19 years. Once again, T and B solver. Number of payments is 12 times 19, 12 months a year times 19 payments. 8% interest rate. 20,000 off the 170 gives you 156,000, and 12 payments per year. Hit alpha enter on the payment value, and it gives you this, which is your answer.